imagine a world so distant, it took us centuries just to confirm it even existed, and then decades more for just one single fleeting visit from a robot explorer. A world wrapped in this deep, mysterious blue where winds rage at supersonic speeds and entire storms like the size of Earth just vanish without a trace.
Yeah, it's an incredible place.
Yeah.
Today we're taking a deep dive into Neptune, the solar system's most distant major planet.
Yeah.
Our mission really is to synthesize everything we know about this enigmatic blue world, from its dramatic discovery all the way to the tantalizing questions it still poses today.
Right.
We want to give you a shortcut, basically, to being well-informed, and hopefully there'll be some surprising facts and maybe a few aha moments along the way.
Definitely. We're going to explore that dramatic discovery, unpack the mythology behind the name, which is fascinating in itself. We'll journey through its wild, violent atmosphere, examine its moons and rings. They're pretty weird, too. And we'll also grapple with the huge challenges and maybe the incredible possibilities of ever actually visiting this ice giant or, even finding life there.
It's a big question.
So, yeah, prepare for an expedition to the very edge of our cosmic neighborhood. Okay, so our journey begins not really with a telescope, surprisingly, but with pencil and paper. Neptune's discovery, it reads like a cosmic detective story. The culprit was unseen, but its influence, undeniable.
It really is a testament to the power of pure mathematics. You see, after Uranus was discovered back in 1781, astronomers started meticulously charting its orbit. And over time, they noticed these subtle, persistent deviations, tiny wobbles, really that just couldn't be explained by the gravity of any known planet.
Ah, okay.
So this anomaly, it strongly hinted at an unseen force, something else out there pulling on Uranus.
So the scientific community, grounded in Newtonian physics, they basically realized there had to be something else out there. A more distant planet whose gravity was tugging on Uranus, causing these weird shifts. I mean, that's an extraordinary hypothesis, right? Predicting a world just based on its gravitational ghost.
Absolutely. And what makes this story truly captivating, I think, is that two brilliant minds, working completely independently on different sides of the English Channel, they arrived at strikingly similar conclusions, almost at the same time.
Wow.
In England, you had John Couch Adams. He began his calculations way back in 1841. He meticulously crunched numbers for years, eventually summarizing his findings for the Astronomer Royal George Airy in a note in October 1845.
But here's where, the human element kind of complicates things. Airy, for reasons we still debate, showed very little immediate interest. He had some technical questions, apparently, but Adams never really followed up properly. It feels like a classic moment of missed opportunity, maybe a communication breakdown.
Could be. Or perhaps just reluctance from the establishment to act solely on theoretical predictions. It's hard to say for sure. Meanwhile, across the Channel in France, Urbain Le Verrier independently took on the same massive task. He developed his own calculations between 1845 and 1846, publishing his first estimate in June 1846. And his findings were incredibly close to Adams's, which, lent immense credibility to this whole idea of a hidden planet. This parallel independent prediction was just a powerful moment in astronomy.
Okay, so this is where the drama really ramps up. Prompted by Leverrier's published work, Airy finally stirred. He encouraged James Challis, the director of the Cambridge Observatory, to actually look for this predicted planet. So Challis starts scanning the skies through August and September of 1846. And here's the kicker. He actually observed Neptune on August 4th and 12th of 1845.
That's right. A full year before it was officially confirmed.
Unbelievable.
He simply didn't recognize it. Apparently, he was hampered by out-of-date star maps, and he was also distracted by other observations, like looking for comets. It's such a poignant reminder that even when the data is right there in front of you, you need the right tools, the right maps, and maybe just a bit of luck or focus to grasp what you're actually seeing.
Talk about being so close yet so far. Wow, so the ultimate confirmation came just a few weeks later then.
Exactly. On September 23, 1846, a German astronomer, Johann Galle, using Leverrier's very precise predictions, pointed his telescope and observed the new planet right near its predicted location. It was stunning, almost immediate vindication for mathematical astronomy.
It must have been an incredible moment.
Oh, absolutely. It was truly profound. It shifted how we understood planetary discovery itself. Until then, new planets were found by, looking through a telescope, stumbling upon them almost. Neptune was the first planet to be predicted into existence purely by the power of mathematical theory and the laws of physics. It didn't just add a new dot to our solar system map. It underscored the incredible predictive capability of Newtonian mechanics and just the sheer intellectual prowess of human scientific inquiry.
So this incredible new world, revealed through sheer brain power, it needed a name that really captured its essence.
And Leverrier, the French astronomer whose predictions led directly to the observation, he suggested Neptune.
Which seems perfect, given that amazing blue color.
It really is incredibly fitting. Neptune, in Roman mythology, is the powerful god of fresh water and the sea. He's the counterpart to the Greek Poseidon. He's often depicted as, this tall, white-bearded figure wielding his iconic trident, symbolizing his absolute dominion over the waters.
I always connect Neptune just with the sea, but I was surprised reading up on this. He had other associations, too.
He certainly did. While yes, he's inextricably linked with fish and all marine life, Neptune was also surprisingly connected to horses.
Horses, really?
Yeah, he was known as Neptunus Equestris, a god of horse racing. And his chariot was famously drawn by these powerful seahorses, or hippocampi. This broader association hints that his influence may be extended beyond just the oceans, connecting to earthly power, maybe even the creation of springs.
A sea god with a thing for horses. That's quite a vivid image. And what about his family tree in the Roman pantheon? His origins?
Well, like many Roman gods, Neptune's backstory is pretty dramatic. He was the son of Saturn and Ops, making him a brother to Jupiter and Pluto. The myth goes that Saturn, fearing his children would usurp him, swallowed them whole right after they were born.
Grim.
Very. But Ops eventually saved them, tricked Saturn, and Neptune joined Jupiter in overthrowing their tyrannical father. When they divided the realms, Neptune drew the seas, Jupiter got the heavens, and Pluto, the underworld.
That's a powerful origin story for a planet that feels so serene and distant from here. Did the Romans celebrate Neptune with any, special festivals?
Oh, yes, they did. The Neptunalia Festival. It was held on July 23rd, right in the scorching heat of summer, often during periods of drought and intense heat. So the timing strongly suggests it was a propitiatory festival, basically, a way to encourage the water god to grant abundant water and relieve the parched land.
Ah, so it wasn't just a party. It was kind of crucial plea for survival, especially in their agricultural calendar. What did people actually do during Neptunalia?
Well, people would build these temporary shelters, often just simple huts made from tree branches and leaves. They'd gather inside to feast and drink, especially spring water and wine, just seeking some relief from the oppressive heat. It was known as a time of general merrymaking, where the usual Roman societal constraints were kind of relaxed.
Sounds fun.
Yeah, and ancient calendars even label it Nep Ludi, which suggests games were included. Probably horse racing, given Neptune's connection to horses and the fact his temple in Rome was near a racetrack.
And the importance of the god himself, that was underlined by the type of sacrifices they offered, wasn't it?
Yes, that's a key point. Neptune was one of only 4 Roman gods alongside Apollo, Mars, and Jupiter to whom a bull sacrifice was considered appropriate. This really highlights his immense importance and power in Roman religion. It signifies a deep, almost strict connection between the deity and the natural world, particularly its life-giving waters.
And his name still echoes today, even beyond the planet itself.
It does. The god's name also inspired the naming of the chemical element, neptunium, discovered shortly after plutonium, which was named for Pluto. So it bridges ancient mythology with modern scientific discovery quite nicely.
Okay, so we've covered Neptune's dramatic discovery, the rich mythology. Now it's time to actually plunge into the planet itself, into its breathtaking and frankly often terrifying realities. When we look at images of Neptune, that striking blue color is the first thing that grabs you.
It really is a defining feature, isn't it? Neptune's faint blue hue comes primarily from traces of methane gas in its outermost atmosphere. Methane absorbs red light and reflects blue light back into space. That's a process called Rayleigh scattering. Same reason our sky is blue, basically.
Okay, methane. But Uranus has methane too, and it looks paler, more cyan.
Exactly. And that's the intriguing part. Neptune is a noticeably deeper, more vivid blue than Uranus. This strongly suggests there's another, as yet unidentified atmospheric component responsible for that richer shade. It's a genuine mystery hidden right there in its color. We still don't know what it is.
Wow, okay. So still some secrets just in the color. Beyond the methane and this mystery ingredient, what's the overall composition of this really dynamic atmosphere?
Well, the upper atmosphere is predominantly gas. It's about 80% hydrogen and 19% helium. Then you have that 1% or so of methane plus trace amounts of other hydrocarbons, and possibly some nitrogen too. Significantly, though, there's no free oxygen, which immediately tells us a lot about the planet's fundamental chemistry and, its prospects for life as we understand it. Pretty much zero.
Right. And speaking of its composition, Neptune's classified as an ice giant. How does that actually distinguish it from the gas giants like Jupiter and Saturn? And what does it tell us about what's inside?
That classification is really crucial. Jupiter and Saturn are mostly just massive spheres of hydrogen and helium, hence gas giants. Neptune, along with Uranus, is an ice giant because its interior is dominated by heavier volatile compounds. We call them ices in planetary science, things like water, ammonia, methane, even though they're not solid ice due to the immense pressure and heat inside. They're actually in a supercritical fluid state.
Okay, so if you could somehow descend into Neptune, what would you find? Is it layered?
Yes, it's believed to be layered. The outer third is basically a mixture of those superheated gases, hydrogen, helium, water vapor, methane.
So definitely no distinct surface to stand on, unlike Earth.
Exactly, no solid surface at all. Beneath this gaseous layer lies the defining feature, the mantle. And again, this isn't solid ice like the name might misleadingly suggest. It's a vast, hot, and incredibly dense region made up of those icy materials, water, methane, and ammonia. Under such extreme pressure and temperature, these materials exist as a supercritical fluid. It's a strange state where the distinction between liquid and gas just blurs. It's also highly electrically conductive.
Wow.
Sometimes it's visualized as a kind of water-ammonia ocean.
A water-ammonia ocean, that sounds utterly alien. What's at the very heart of this blue behemoth, then?
Well, deep down at the very center, scientists believe there's a rocky core, probably made of silicates, iron, and nickel, and roughly 1.2 times the mass of the entire Earth.
So an Earth-sized rocky core buried inside.
Pretty much. But the conditions within are just beyond anything we experience. Temperatures are thought to reach 5,400 Kelvin. That's over 5,100 degrees Celsius, or 9,000 Fahrenheit. And the pressures soar to an astonishing 7 million times the pressure of Earth's atmosphere at sea level.
7 million times.
Yeah.
It's just mind-boggling. It's hard to even comprehend.
It really is. These are truly unimaginable forces at play.
And this incredible internal heat, it seems to power some pretty extreme weather up top, doesn't it?
It absolutely does. Despite Neptune being so incredibly far from the sun, it possesses a powerful internal heat source. It actually radiates more than twice the energy it absorbs from the sun. And this internal heat engine is the driving force behind its incredibly dynamic and violent atmosphere. It makes Neptune a world of constant, ferocious change.
And when you say violent, you mean supersonic winds, literally the fastest in our entire solar system.
Indeed. Neptune holds the record. We've measured winds at up to 2,100 kilometers per hour. That's roughly 1,300 miles per hour, whipping around the edges of its giant storms. Some estimates even push that figure closer to 1,500 miles per hour. For context, that's faster than the speed of sound here on Earth.
Wow.
The clouds at its equator can complete a full rotation around the planet in just 18 hours. It's truly a planet where the atmosphere itself feels like it's trying to escape.
That speed is just astonishing. And speaking of storms, Voyager 2 gave us our first proper look at the iconic Great Dark Spot.
Yes, the Great Dark Spot, or GDS. It was this colossal, elliptically shaped storm system, an anticyclone, actually. Voyager 2 first captured it in 1989 down in Neptune's southern hemisphere. It was roughly the size of Earth, measuring about 13,000 by 6,600 kilometers. And visually, it did look quite similar to Jupiter's Great Red Spot.
What exactly was it, though? Just a big storm cloud?
Scientists believe it was essentially a massive hole in Neptune's upper methane cloud deck. It allowed us to peer deeper into the atmosphere, revealing darker layers below, hence the name dark spot.
But unlike Jupiter's Great Red Spot, which seems almost permanent, Neptune's GDS didn't stick around, did it?
No, and this is where the mystery of Neptune's weather really deepens. Jupiter's Great Red Spot has persisted for centuries, we think. But Neptune's dark spots, they're ephemeral. Just 5 years after Voyager 2 saw the GDS, the Hubble Space Telescope turned its gaze on Neptune in 1994, and the Great Dark Spot had completely vanished.
Gone. Wow. Just gone.
That cool? Yep. It revealed a fundamental truth about Neptune. Its great storms are transient features, often lasting only a few years. It's a much more dynamic and rapidly changing system than Jupiter's.
But other dark spots have popped up since then, haven't they?
That's right. Voyager 2 also saw a smaller companion spot called Dark Spot 2, which had also disappeared by 1994. But later, in 1994, Hubble observed a different dark spot that appeared in Neptune's northern hemisphere, NGDS 94. And even more recently, in 2020, Hubble spotted a fragment, nicknamed Dark Spot Jr., breaking off from a larger storm that had appeared in 2018, NGDS 2018.
Dark Spot Jr., that's kind of cute.
Well, maybe. This fragment's appearance actually coincided with the larger storm reversing its usual northward drift. It led scientists to speculate that maybe shedding these fragments is a mechanism that stops the storms from migrating too close to the equator, where they tend to dissipate.
Huh. So these massive storms are constantly forming, shifting, maybe shedding pieces, and then dissipating. Do we have any clear idea how they form in the first place?
The exact formation mechanism is still a bit of a puzzle, honestly. However, observations suggest that an increase in bright companion cloud activity typically precedes the visible appearance of these dark spots by maybe 2 to 3 years. As for why they disappear, one idea is that these companion clouds might eventually reach the storm center, block the blue wavelengths of light from deeper down, and essentially make the dark spot appear to vanish from our view. But we need more data.
Fascinating. Okay, beyond the wild weather, Voyager 2 also delivered some groundbreaking insights into Neptune's magnetic field, didn't it?
Oh, absolutely. Voyager 2 discovered that Neptune's magnetic field is highly unusual. Really weird, actually. It's dramatically tilted about 47 degrees relative to the planet's rotation axis, and it's also significantly offset from the planet's physical center.
Tilted and offset, that sounds chaotic.
It is. This bizarre, off-kilter configuration is quite unique among the planets in our solar system. It provides crucial clues about Neptune's interior structure, particularly that conductive water-ammonia mantle, and how dynamos might generate magnetic fields in these ice giants. It's very different from Earth's relatively neat field.
And speaking of unique features, Neptune does have a ring system, but it's nothing like Saturn's bright, iconic rings, right? It's much fainter.
Very much so. The first hints of rings around Neptune actually came back in 1968 through stellar occultations. More analysis in the early 1980s even suggested the rings might be incomplete, like arcs. But it was Voyager 2 in 1989 that finally provided the first clear, definitive images of Neptune's faint and dusty ring system, confirming they were complete rings, albeit very faint.
So we're definitely not talking about those bright, icy bands like Saturn has. What are Neptune's rings actually made of?
Neptune's system has 5 main rings, and they're composed primarily of very dark dust particles, possibly mixed with some ice particles, but likely coated with a dark, carbon-based substance, which makes them incredibly hard to see. They reflect very little light.
And the most mysterious part of these ring arcs, right? Clumps of material within the rings.
Precisely. The outermost and narrowest main ring, called the Adam's ring, contains these enigmatic clumps of dusty material. Voyager 2 famously imaged 4 prominent arcs, and they were named Liberté, Égalité, which turned out to be 2 distinct arcs, Fraternité, and Courage, very French, reflecting Leverrier's role.
But basic physics, orbital mechanics, would predict these clumps should spread out evenly around the ring pretty quickly, shouldn't they? Why are they clumped together?
That's the puzzle. Theory definitely predicts these clumps should disperse over a relatively short timescale. The leading hypothesis is that they are gravitationally confined or shepherded by the small moon Galatea, which orbits just inside the Adam's ring. Its gravity might be creating stable zones where the dust can accumulate.
A shepherd moon, like some of Saturn's moons do.
Exactly. However, observations made since 1989 suggest that even with Galatea's influence, these arcs might not be perfectly stable. They seem to be slowly decaying or changing, with some having faded quite significantly since Voyager first saw them. It's another testament to the dynamic and still somewhat mysterious nature of the entire Neptunian system. Things are clearly still evolving out there.
It's just incredible to think that almost everything we know in detail about Neptune, its wild atmosphere, those faint rings, its weird moons, comes primarily from one single fleeting visit. That visit, of course, was by the legendary Voyager 2.
Yeah, the profound impact of Voyager 2 really cannot be overstated. It launched way back in 1977, embarking on this unprecedented grand tour of the outer planets using a rare planetary alignment. Its closest approach to Neptune came on August 25, 1989. It passed a mere 3,408 miles. That's incredibly close above Neptune's North Pole. This was the final planetary encounter of its historic mission, a true grand finale that basically rewrote our textbooks on the outer solar system.
And in just those few hours of close approach, it completely transformed our understanding of a world that, until then, was really just a fuzzy blue dot seen through Earth-based telescopes.
Absolutely. In that brief, crucial window, Voyager 2 returned over 9,000 images and just a treasure trove of other scientific data. It tremendously increased our knowledge of the most distant major planet in the solar system. The spacecraft was essentially a flying laboratory, packed with these amazing instruments for the time that allowed us to truly see Neptune and its system for the first time.
Rather than list all the instruments, maybe tell us about how a couple of the key ones specifically revolutionized our understanding of Neptune.
Sure. Well, the Advanced Imaging Science System, for instance, its cameras, gave us our first clear, detailed pictures of the Great Dark Spot. That revealed this colossal storm system, unlike anything we'd managed to resolve from Earth. It showed us the dynamic nature of Neptune's atmosphere firsthand. And crucially, the magnetometers aboard Voyager 2 were vital. They were the instruments that unveiled Neptune's bizarre, highly tilted and offset magnetic field. That completely reshaped our understanding of its deep interior and how magnetic fields are generated in ice giants. Without those specific instruments, those revolutionary discoveries simply wouldn't have happened.
And it didn't just confirm new things, it also definitively solved a really long-standing cosmic mystery, didn't it? About Planet X.
Yes, that was one of Voyager 2's most profound, maybe unsung, achievements. For decades, astronomers had hypothesized about an undiscovered planet beyond Neptune, this Planet X, mainly to account for those perceived irregularities in Uranus's orbit that led to Neptune's discovery in the first place, but some thought there might still be discrepancies. By providing the first truly accurate measurement of Neptune's mass, Voyager 2's data definitively showed that Neptune's gravitational pull fully accounted for Uranus's orbital path. No leftover wobbles.
Okay.
This conclusively disproved the need for any massive Planet X out there to explain Uranus's orbit. It was a huge scientific mic drop moment, closing a chapter that had been open for nearly 150 years.
That's a massive clarification. But getting all that incredible data back from literally billions of miles away, that sounds like an engineering nightmare. How on earth did they pull that off?
Oh, the sheer scale of communicating across the cosmos is just immense. Radio signals from Voyager 2, even traveling at the speed of light, still took 4 hours, 246 minutes, to be precise, just to reach Earth from Neptune. And by the time they arrived, these signals were incredibly weak. We're talking like a fraction of a billionth of a watt, like a whisper across a vast cosmic ocean about 4.6 billion kilometers wide.
4 hours just for the signal to arrive, that really puts the distance into perspective. How did NASA manage to even hear that whisper?
Well, to ensure they could hear Voyager loud and clear and maximize the precious data transmission rate, NASA's Deep Space Network, the DSN, underwent a significant expansion specifically for the Neptune encounter. Their largest antennas, huge dishes in Madrid, Canberra, and Goldstone, California, were enlarged from 64 meters to 70 meters in diameter. Just that extra size made a big difference. They also linked up with non-DSN antennas, like another big 64-meter dish in Parkes, Australia, and even multiple 25-meter antennas at the Very Large Array in New Mexico, using them all together. All of these dishes essentially worked in concert, acting as one giant, incredibly sensitive ear pointed towards Neptune.
Wow, that's a massive global collaborative effort just to listen in. And the spacecraft itself required unbelievable precision during the flyby, didn't it?
Absolutely. During that closest approach, the engineering team at JPL had meticulously programmed Voyager 2's tiny thrusters. They had to gently fire them in tiny bursts to rotate the spacecraft, keeping its cameras and other instruments precisely focused on its targets, Neptune and its fascinating moon Triton, all without significantly disrupting its overall speed and trajectory. Achieving that level of precision while hurtling through space at tens of thousands of miles per hour across billions of miles, it really stands as an absolute engineering marvel.
You can just imagine the atmosphere at JPL during that week in August 1989. What was it actually like? Must have been electric.
Reports say the atmosphere was absolutely electric. As the images, taking those 4 long hours to arrive, slowly streamed back to Earth, Voyager team members would crowd around the few available computer monitors. Remember, this was way before the widespread internet, so these limited screens were the only places to witness these discoveries as they literally unfolded, pixel by pixel sometimes. There were daily press conferences sharing new findings with an eager world, and there was even a special Voyager All-Night program broadcast on TV during the closest encounter period. Vice President Dan Quayle visited JPL, and Chuck Berry, whose song Johnny Be Good is famously on the golden record aboard Beezus. Voyager even played at the celebration party afterwards. It was a moment of immense public excitement and collective pride, a truly shared human experience of exploration.
That sounds amazing. A real cultural event celebrating scientific triumph. And Voyager 2 didn't just stop at Neptune, did it? It kept going into the great beyond.
That's right. After its incredibly successful Neptune encounter, Voyager 2 transitioned into its interstellar mission phase. It eventually crossed the heliopause, that's the boundary marking the edge of our sun's direct influence, the edge of the heliosphere bubble, and entered true interstellar space in late 2018. Voyager 1 had done it a few years earlier.
Humanity's first robotic emissaries stepping into the cosmic ocean. What are they doing now, Voyager 1 and 2?
They continue, incredibly, to send back invaluable data on the weather and conditions from this truly uncharted region. It's filled with cosmic rays and plasma from interstellar space, material from exploded stars. This provides humanity's first direct measurements from outside our solar system's protective bubble. The Voyager data also complement other missions studying that boundary, like NASA's IBEX, and helps inform future projects like the IMAP probe, which launched in 2024, continuing this journey of discovery into our place in the galaxy.
And of course, both Voyagers carry that iconic symbol of humanity's aspirations, the golden record.
Yes, each spacecraft carries a gold-plated copper disc. It's essentially a time capsule containing sounds and images selected to portray the diversity of life and culture on Earth. It's a message in a bottle, really, cast into the cosmic ocean, intended for any extraterrestrial civilization that might someday encounter the spacecraft, billions of years from now, perhaps. A symbol of who we were and what we hoped for.
Okay, so Voyager 2 gave us that incredible, albeit brief, look at Neptune itself. But what about its family? The moons of Neptune are a really diverse and mysterious bunch.
They certainly are. Neptune currently has 16 known moons. The latest one, Hippocamp, was only found in 2013, hiding in Hubble images from years earlier. And fittingly, keeping with the theme, all of them are named after Greek or Roman mythological characters associated with Neptune, Poseidon, or other ocean and water deities. It ties them nicely to the planet's namesake.
It's just incredible that Neptune's very first moon, its largest one, was discovered almost immediately after the planet itself, like within weeks.
That really is an incredible piece of astronomical history.
Yeah.
William Lassell, who was an English merchant, or a brooder actually, and a very dedicated amateur astronomer, he funded and built his own large telescopes with his brewing fortune, and he discovered Triton on October 10th, 1846. That was just 17 days after Neptune itself was officially discovered by Johann Galle using Leverrier's predictions.
Wow, 17 days.
Yeah. And for over a century, Triton was known simply as the satellite of Neptune because it was the only one known until a much smaller second moon, Nereid, was finally found in 1949 by Gerard Kuiper.
Triton really sounds like the star of Neptune's moon system, though. It's described as this enigmatic main moon with some truly bizarre characteristics.
Triton is definitely the standout. It's by far Neptune's largest moon, and it was also the last solid body explored up close by Voyager 2 during its 1989 flyby. What makes Triton so enigmatic, so weird, is its highly unusual orbit. It's retrograde.
Retrograde meaning backwards.
Exactly. It orbits in the opposite direction to Neptune's rotation. And its orbit is also dramatically inclined, about 157 degrees relative to Neptune's equator. This is extremely rare for a large moon in our solar system.
And a retrograde orbit like that tells us something really important about Triton's past, doesn't it?
It absolutely does. Its retrograde orbit is the smoking gun evidence, really. It strongly suggests that Triton wasn't formed in situ alongside Neptune from the same swirling disk of gas and dust. Instead, it must have been a dwarf planet, maybe similar to Pluto, cruising through the outer solar system that got captured by Neptune's immense gravitational pull at some point in the distant past.
Captured. That sounds like it would have been a pretty violent event.
Oh, incredibly energetic and violent. This capture event would have led to a really dynamic and complex history for the moon, likely involving intense tidal forces as its initial eccentric orbit circularized over millions of years. These forces would have pumped huge amounts of heat into its interior.
And its surface reflects that dynamic past. It's not just some dead, heavily cratered world like our moon.
Far from it. Voyager 2 images revealed a surface with relatively few impact craters, which tells us it must be quite young, geologically speaking. It's clearly being constantly remodeled by internal processes. And the most astonishing thing Voyager saw? Cryovolcanoes, active geysers.
Cryovolcanoes?
Yeah.
Like ice volcanoes?
Essentially, yes. Voyager's images revealed geysers spewing plumes of dark material thought to be nitrogen gas laced with fine, dark organic particles, maybe methane derivatives up to 5 miles or 8 kilometers high into Triton's incredibly thin atmosphere. This material then falls back down and deposits onto the surface, creating those dark streaks Voyager saw, even at the incredibly frigid surface temperatures of minus 392 degrees Fahrenheit or minus 200 Celsius.
Geysers of nitrogen ice and dust erupting at those temperatures? That sounds like something straight out of science fiction. How is that even possible?
It truly does. The exact mechanism isn't fully understood, but it's likely driven by seasonal heating from the faint sunlight-warming subsurface nitrogen ice, causing it to sublimate into gas and build up pressure until it erupts through vents. This cryovolcanism is a clear sign of ongoing geological activity, even today. Furthermore, a large portion of Triton's surface shows evidence of past melting and resurfacing, features like cantaloupe terrain, vast frozen plains. This was possibly due to that intense tidal heating during and after its capture by Neptune. That heat could have potentially kept its interior, or at least its subsurface layer, liquid for as long as 1 billion years after its capture.
1 billion years of potentially liquid interior. And its unusual orbit also means it experiences really dramatic seasonal changes, right?
Yes, exactly. Because of its highly inclined orbit relative to Neptune and Neptune's own orbit around the Sun, Triton's poles and equator alternately face the Sun over Neptune's long year. This likely causes dramatic seasonal shifts, driving changes in its tenuous nitrogen atmosphere and the migration of surface ices. When Voyager 2 flew by in 1989, it observed a bright nitrogen and methane ice cap covering Triton's south pole, which was facing the Sun at the time.
So, okay, we have ongoing activity, evidence of past melting, potential internal heat from capture, maybe even radioactive decay. Does Triton hold any real astrobiological potential? Could there be life?
This is really the critical question, and why Triton is such a high-priority target for future exploration. The possibility of a subsurface ocean of liquid water potentially kept liquid by residual tidal heating, salts acting as antifreeze, and insulated by a thick icy shell makes Triton a prime target for astrobiological investigation. It's widely considered the most compelling argument for the potential of life, or at least habitable conditions, within the entire Neptunian system, far more likely than on Neptune itself.
Right. Okay, so beyond the superstar Triton, Neptune has this whole family of other moons. You mentioned irregular moons orbiting close in, and more distant, irregular ones. What can you tell us about them?
Yeah, Neptune's moons are broadly classified. You have the regular moons, which have relatively circular orbits close to Neptune's equatorial plane, suggesting they probably formed alongside the planet or from debris after Triton's capture disrupted things. Then you have the irregular moons, which have much more eccentric, inclined, and often distant orbits, suggesting they, like Triton perhaps, were captured objects. The irregular moons include Naiad, Thalassa, Despina, Galatea, and Larissa. And Proteus, the big one.
And these inner moons, they seem really tangled up with Neptune's faint ring system, don't they?
Absolutely. They are very closely associated with Neptune's dusky rings, and some likely act as shepherd moons, gravitationally confining the ring particles. For instance, Naiad and Thalassa orbit between the Galli and Leverrier rings. Despina might actually be a shepherd moon for the Leverrier ring itself, helping to keep its edges sharp. And Galatea, as we mentioned, orbits just inside the Adams ring, and it's thought to play a key role in confining those mysterious ring arcs.
So they're not just passively orbiting, they're actively sculpting the rings. What's their long-term fate, though, being so close to Neptune?
Well, Naiad, Thalassa, Despina, and Galatea are all orbiting within Neptune's synchronous orbit limit. That means they orbit Neptune faster than the planet itself rotates. Because of tidal forces, specifically tidal deceleration, these moons are slowly transferring their orbital energy to Neptune. This causes their orbits to decay, spiraling inwards. Yeah, it means they will eventually, probably billions of years from now, either crash directly into Neptune's atmosphere or get torn apart by its immense gravitational forces once they cross the Roche limit, potentially forming new, temporary rings from their debris.
A rather dramatic end. What about Proteus? You mentioned it's the largest regular moon.
Yes, Proteus is quite interesting. It's the largest of the regular moons, and Neptune's second largest moon overall after Triton, measuring about 260 miles or 420 kilometers in diameter. It's roughly spherical, but it's not perfectly round. It actually resembles a slightly faceted polyhedron, kind of lumpy. Its shape tells us it's probably right at the limit, the largest size a body of its density can be, without its own gravity being strong enough to pull it into a perfect sphere. It's heavily cratered, too, indicating an old surface.
And Larissa, another inner moon, it had kind of a unique discovery story, too.
Yes, Larissa was actually initially spotted back in 1981, but indirectly. Astronomers observed its occultation of a star it passed in front of a star, causing it to dim briefly. At the time, this dimming was mistakenly attributed to those hypothetical ring arcs. It was only when Voyager 2 flew by in 1989 that its images confirmed Larissa's existence as a distinct moon, clarifying that it was the moon causing that stellar dimming, not just ring material.
And what about the other irregular moons? Way out there, like Nereid and that tiny one, Hippocamp?
Right, the irregulars are a whole different population. Nereid, discovered in 1949, is famous for having one of the most eccentric orbits of any satellite in the entire solar system. Its eccentricity is 0.75. This means its furthest point from Neptune, apoapsis, is about 7 times further away than its closest point, periapsis. It follows this incredibly long, stretched-out path.
Wow, 7 times difference. That's a wild orbit.
It really is. And then there's Hippocamp, the baby of the family, discovered in 2013. It's Neptune's smallest known moon, maybe only 20 miles across. It orbits very close to Proteus, and might actually be a fragment chipped off Proteus by a large impact long ago. Each of these moons, regular or irregular, big or small, really tells a unique story about the complex, dynamic, and often chaotic history of planet formation and evolution in the outer solar system.
Okay, so we've taken this incredible deep dive into Neptune. We've gone from its ghostly mathematical discovery and mythology through its wild atmosphere, its strange rings, its fascinating moons. But now it's time to tackle the ultimate questions. Can we ever truly visit Neptune with humans? And could life possibly exist there, or maybe around there? Let's start with human missions. Is it even remotely feasible for us to travel that far?
That's really the crux question of scale and logistics, isn't it?
Right.
Neptune is way out there, approximately 30 astronomical units from the sun. That's 30 times the Earth's sun distance, about 4.5 billion kilometers or 2.8 billion miles. A journey there is just incredibly long. Remember, Voyager 2, even using that rare planetary alignment for gravity assist to gain speed, still took over 12 years to reach it, launching in 1977 and arriving in 1989.
12 years for a robotic probe. Sending humans, that's an entirely different ballgame, isn't it? Even for future robotic probes, the travel times are still measured in many years.
Absolutely. Even with advanced propulsion concepts being explored, estimated travel times for robotic probes designed specifically for Neptune are still projected to be around 8 to 13 years. For instance, a mission concept floated called Next Step projected maybe an 8.7-year journey using gravity assists. A direct transfer using a classic Hohmann transfer orbit, the most fuel-efficient path without assists, would take an astonishing 30.7 years one way.
30 years. Okay, so human missions would compound these challenges just exponentially.
They really would. Human missions introduce a whole host of additional incredibly complex challenges that probes just don't have to deal with. Firstly, there's space radiation. Outside Earth's protective magnetosphere, especially in deep space, astronauts are exposed to constant high-energy cosmic rays and solar particle events. This is invisible, highly hazardous, and poses significant long-term health risks, increased cancer risk, potential neurological damage, cataracts.
Right, the health risks alone are huge.
Immense. Then you have the profound psychological effects of extreme isolation and confinement, spending years, maybe decades, cooped up in a small spacecraft billions of miles from home. That leads to behavioral and psychological responses that need incredibly careful management. Team cohesion, mental health support, it's critical.
Not to mention just the sheer distance from Earth. You are truly fundamentally on your own out there.
Precisely. That distance means severely limited communication. Forget real-time conversations. You're talking hours for a message round trip. There's absolutely no possibility of sending new supplies quickly or providing immediate complex medical care beyond what's on board. Self-sufficiency becomes not just paramount, but an absolute matter of survival. Astronauts would also have to contend with transitioning between different gravity fields, Earth launch, zero-G cruise, maybe artificial gravity, then maneuvering near Neptune. Adjusting to these altered gravitational loads affects muscles, bones, cardiovascular systems, even balance organs over very long durations.
And just keeping the environment inside the ship stable.
Exactly. Maintaining a safe, stable, breathable ecosystem within a hostile, completely closed environment for years on end is an ongoing fragile balancing act. Meticulously managing temperature, pressure, humidity, lighting cycles, noise levels, filtering air and water, controlling microbes, monitoring astronaut immune responses. It's an incredibly complex life support challenge.
So we need unbelievable advancements in pretty much every system imaginable. What about just getting there fast enough for humans? Is that even possible?
That's arguably the biggest hurdle of all, energy and propulsion. Reaching Neptune in a time frame suitable for humans, say, less than a decade, ideally much less would require reaching truly enormous speeds, significant fractions of the speed of light, ideally. And achieving those speeds requires truly mind-boggling amounts of energy. Our current chemical propulsion technologies are simply nowhere near adequate for human missions to Neptune within any kind of reasonable time frame. They just can't provide enough thrust for long enough without needing impossible amounts of fuel.
So what about advanced propulsion, nuclear rockets, fusion? That warp drive stuff.
Well, proposed advanced technologies like nuclear pulse propulsion, Project Orion style, Various nuclear thermal rocket designs, or even fusion rockets, are theoretically much more powerful. But they face immense technical challenges, safety concerns, and would require enormous spacecraft. And more theoretical concepts like the Alcubierre warp drive are purely speculative at this point, possibly requiring physics we don't even understand yet, like negative mass energy. They are not practical engineering concepts currently.
Okay. So the verdict for human missions to Neptune, realistically, is not great.
Unfortunately, yeah. The realistic verdict, based on current and foreseeable technology, is that human missions to Neptune are currently far beyond our grasp. Many experts opine it's actually improbable that humans will ever explore much beyond Mars or maybe the asteroid belt within the next century or two, primarily due to these immense energy requirements for rapid travel, the long travel times even with advanced concepts, the profound health risks, and just the sheer scale of technological and financial investment required for multi-year, self-sufficient deep space voyages. Sending robots is vastly more feasible and cost-effective.
Okay, so if humans probably can't go, what about life on Neptune itself? Could that wild, turbulent blue world deep inside actually harbor any kind of life as we know it?
Right, putting aside the moons for a second, life on Neptune itself. The resounding answer, based on everything we currently understand about life and planetary science, is a pretty definitive no. The environment on Neptune is considered utterly, completely inhospitable to life as we know it.
Why such a definitive no? What are the absolute deal breakers for life on Neptune?
Well, there are numerous really fundamental reasons. Firstly, as we discussed, Neptune is an ice giant. It lacks a solid planetary surface. There's simply no ground, no stable substrate for life to form, anchor itself, or develop stable ecosystems upon. It's just gas getting denser and denser until it becomes that weird fluid mantle. Secondly, the extreme temperatures are lethal at both ends. The cloud tops are frigid, way below freezing, around -214 Celsius or -353 Fahrenheit. But as you go deeper, the temperatures and pressures skyrocket, reaching thousands of degrees and millions of atmospheres, conditions that would crush and incinerate any known organism instantly.
And the atmosphere itself isn't exactly breathable for anything we're familiar with, right?
Right.
No oxygen.
Precisely. The atmospheric composition is predominantly hydrogen and helium, with some methane. There's no free oxygen, which is essential for the complex, energy-intensive metabolism of terrestrial life, especially complex life. Moreover, the sheer violence of the planet's weather patterns, those supersonic winds, the turbulent atmospheric convection, huge storms forming and dissipating, would make any kind of stable existence impossible. Any hypothetical organism would be violently transported between utterly lethal temperature and pressure zones in possibly mere moments. There's no stable niche.
Right.
And as we mentioned, the crushing pressures in the interior are judged to be far too extreme to allow any complex chemistry associated with life to persist.
So all those cool sci-fi ideas about, like, giant floating life forms and gas giant atmospheres, Carl Sagan speculated about them for Jupiter, probably don't apply to Neptune.
While those ideas are fascinating thought experiments, and Sagan's floater-shunter-sinkers for Jupiter were based on some plausible chemistry for Jupiter, the specific conditions on Neptune make it much less likely. Especially its extreme cold in the upper atmosphere where pressures might be manageable, the complete lack of free oxygen, and just the relentless violence of its weather. The conditions seem far too hostile and dynamic even for hypothetical exotic life forms.
Okay, so if not Neptune itself, is there any hope for life anywhere in the Neptunian system? You mentioned Triton earlier.
Yes, exactly. If there's a compelling argument for life, or at least habitable conditions, in the Neptune system, it lies not on the planet Neptune, but almost certainly on its largest moon, Triton.
Back to Triton with its cryovolcanoes and that young, active surface.
Precisely. All that evidence, the young cryovolcanically active surface, the signs of past melting, the potential for residual internal heat from its capture and radioactive decay, it all points strongly toward the possibility of a subsurface ocean of liquid water. This potential subsurface ocean, perhaps kilometers below the icy crust, shielded from the harsh surface conditions and potentially containing dissolved minerals and energy sources. That makes Triton a prime target for future astrobiological investigation. Its unique characteristics are a key driver for many proposed future missions to the outer solar system, specifically looking for signs of habitability, if not life itself.
Okay, so our deep dive into Neptune has revealed this world of incredible extremes, profound mysteries.
Yeah.
We've gone from its ghostly mathematical discovery right up to Voyager 2's breathtaking yet frustratingly brief flyby. But our knowledge, it still feels fundamentally limited, doesn't it? Just snapshot.
That's absolutely the crux of it. Our current understanding of the entire Neptunian system is fundamentally just a tantalizing snapshot. It's based almost entirely on Voyager 2's single brief encounter way back in 1989, supplemented by decades of painstaking but limited long-distance observation from Earth and Earth orbit with telescopes like Hubble. This fleeting glimpse, while utterly revolutionary at the time, definitely left us with more compelling mysteries than firm answers.
So what are some of those really profound questions still echoing across the cosmos, the ones compelling us to think about going back to Neptune?
Oh, it's those big unanswered questions that really fuel our desire to return. We still don't precisely understand the nature and depth of Neptune's powerful internal heat source. What is the mechanism generating so much more heat than it receives from the distant sun? It's the very engine driving those impossible supersonic winds. We also still haven't identified that unknown atmospheric component, the chromophore, that gives Neptune its deeper, more vivid blue color compared to its near twin, Uranus. Cracking that is a key piece of the atmospheric chemistry puzzle, hinting at processes we just don't yet grasp.
And those great dark spots appearing and vanishing, they still hold secrets, right? They're not just random weather patterns.
Absolutely. We need to understand the complete life cycles of these great transient dark spots. What drives their formation, their evolution, their decay? What do their ephemeral natures truly reveal about the inner workings, the energy transport, the deep dynamics within ice giant atmospheres? Are they surface features or windows into deep convective processes? And then, most profoundly perhaps, there's Triton. Does it truly harbor a subsurface ocean of liquid water today? And if so, is that ocean a potentially habitable environment? Could it even harbor life, past or present? These are fundamental questions about the limits of life in the solar system that simply cannot be answered from Earth. We have to go there.
So it's clear scientifically we need to go back. What would the next generation of missions actually look like? What are scientists proposing?
The scientific consensus, strongly articulated in things like the U.S. Planetary Science Decadal Survey, is that a dedicated orbiter mission, equipped with modern, highly sensitive instruments, is the essential next logical step. An orbiter would allow us to truly understand planetary formation in the outer solar system by comparing Neptune and Uranus, study the unique atmospheric dynamics driven by Neptune's internal heat in detail over time, and, crucially, investigate Triton's astrobiological potential thoroughly. A flyby just isn't enough anymore.
Have there been specific mission concepts proposed over the years?
Yes, definitely. Going back to 2003, NASA's Vision mission studies included a detailed concept for a flagship-class Neptune orbiter with probes mission, aiming for the kind of comprehensive science return we got from Cassini at Saturn, an extended in-depth study of the entire system. More recently, though not selected for funding, there was the proposed Argo mission concept. That was envisioned as a New Frontiers-class flyby spacecraft that would have launched around 2019, visited Jupiter, Saturn, then Neptune and Triton around 2029, before heading to a Kuiper Belt object. A faster, cheaper flyby, but still limited.
And other countries are looking seriously at Neptune too, aren't they? China, for instance.
Indeed. The China National Space Administration, CNSA, has been studying a concept for a pair of Voyager-like interstellar probes called Shenzhou, or Interstellar Heliospheric Probes, IHP. The second probe in this concept, IHP-2, is currently planned, notionally, to fly by Neptune around January 2038. It would pass incredibly close, just 1,000 kilometers above the cloud tops, and potentially carry an atmospheric impactor or small probe to analyze its composition directly. It would then continue out into the Kuiper Belt and towards the heliosphere's tail, exploring truly uncharted regions.
That's a very bold vision. So what kind of instruments, what components would these next-generation missions ideally need to carry to answer those burning questions about Neptune and Triton?
Well, a dedicated orbiter would be the core platform, designed to study the entire Neptune system, its interior structure, atmosphere, moons, rings, and magnetosphere for maybe 2 or more years, allowing us to see changes over time. Critically, an atmospheric probe is almost always highly recommended. This would be designed to detach from the orbiter and descend deep into Neptune's upper atmosphere, ideally reaching pressures of at least 10 bars, or 10 times Earth's sea level pressure.
What would the probe measure?
Its main goal would be to directly measure crucial gas compositions, especially noble gases like argon, krypton, xenon, and key isotope ratios like deuterium to hydrogen. These act as unique fingerprints that tell us about the conditions in the early solar nebula where Neptune formed, constraining planetary formation models. It would also measure temperature, pressure, density profiles, wind speeds, and look for distinct cloud layers.
So really digging deep into the planet's birth story and structure.
Exactly. Another novel instrument proposal often mentioned is a Doppler imager. This would essentially stare at the planet and look for subtle atmospheric oscillations, like sound waves bouncing around inside, caused by motions at different depths. This could reveal Neptune's interior structure in a way similar to how helioseismology studies the Sun's interior. We'd also need a sophisticated magnetometer, not just for Neptune's field, but specifically to search for induced magnetic fields around moons like Triton. Detecting such a field, which would vary as Triton moves through Neptune's main field, would be incredibly strong evidence for a present-day electrically conductive layer inside Triton, most likely a salty liquid water ocean. It's the same technique used by the Galileo spacecraft to infer oceans at Europa and Ganymede.
That sounds like a key experiment for Triton, and obviously better cameras.
Oh, absolutely. Modern high-resolution cameras and imaging spectrometers would be crucial. Cameras for detailed mapping of the surfaces of Triton and the other moons, revealing their geological history in far greater detail than Voyager could. And imaging spectrometers to map surface composition, potentially identifying materials erupted from their interiors, like on Triton, or understanding the dark stuff on the rings and inner moons. These modern instruments would provide a level of detail far beyond what Voyager 2 captured, enabling us to truly understand their past and present activity.
These missions sound incredibly ambitious and obviously incredibly important scientifically. What are the biggest hurdles, the main challenges we still need to overcome to actually make them a reality?
The hurdles are indeed monumental. They require significant technological leaps in some areas, and perhaps more importantly, a sustained multi-generational commitment. Travel time, as we discussed, remains a primary challenge. Even with optimal gravity assists from Jupiter, which only line up roughly every 12 years, you're still looking at a decade-plus journey just to get there. That puts immense demands on spacecraft longevity and mission planning.
And power is always a huge problem that far out from the sun. Solar panels just wouldn't cut it at Neptune, right?
Correct. At Neptune's immense distance, sunlight is about 900 times fainter than at Earth. Solar panels large enough to power a flagship orbiter would be impractically massive and complex. So missions must rely on radioisotope thermoelectric generators, or RTGs, which convert heat from the natural radioactive decay of plutonium-238 into electricity. These systems are reliable and have flown for decades, but they are heavy. The fuel supply, Pu-238, is limited and expensive to produce, and their power output naturally degrades over the long cruise phases. Advancements in next-generation radioisotope power systems, RPS, are really needed to provide more efficient, longer-lasting power for ambitious future outer planet missions.
Then there's the actual physics of getting into orbit once you finally arrive after that decade-long trip. That must be a massive braking maneuver.
It is. Propulsion and orbital insertion are huge challenges. You arrive at Neptune at very high speed after the long journey, so the spacecraft must perform a massive braking burn using a large chemical propulsion system just to be captured into orbit. This requires carrying a lot of heavy propellant, which in turn requires a powerful, expensive launch vehicle from Earth. Researchers are exploring advanced propulsion options to help here. Highly efficient solar electric propulsion using ion engines could shorten trip times or allow larger payloads for the inner part of the journey, but thrust is low. More advanced concepts like nuclear electric propulsion using a small fission reactor to power ion engines, or nuclear thermal propulsion using a reactor to directly heat propellant could significantly reduce travel times, perhaps down to 6 to 8 years. But these face their own technical hurdles, development costs, and safety considerations. Aerocapture using Neptune's upper atmosphere to break air braking is another potential method being studied to save propellant mass for orbital insertion.
Lots of challenges there. And once we're finally in orbit, getting all that amazing detailed data back to Earth across billions of miles must be incredibly difficult, like sipping data through a tiny straw.
That's another critical bottleneck.
Yeah.
Data transmission. The vast distances severely restrict data rates due to the inverse square law weakening the signal. For instance, communicating with a large 70-meter DSN antenna from Neptune might only achieve data rates around 7 kilobits per second, maybe a bit more with advanced coding. That's incredibly slow for sending back high-resolution images and the vast amounts of data modern scientific instruments can generate. Optical deep space communications, using lasers instead of radio waves, holds the potential for vastly increased bandwidth, maybe 10 to 100 times current rates. But that technology still needs to mature significantly for routine use at outer planet distances, including needing dedicated ground stations and overcoming pointing challenges.
So ultimately, launching one of these flagship missions to Neptune, it all comes down to sustained commitment and, frankly, cost, doesn't it?
Ultimately, yes. These are truly monumental, multi-generational undertakings. They require significant, sustained financial investment, often billions of dollars over decades, and they demand long-term planning and political will. often stretching a quarter century or more from initial concept studies to actually getting data back from Neptune orbit. That's not unusual for outer planet flagship missions. It's really a profound testament to humanity's scientific ambition, our drive to explore, that we continue to seriously plan and pursue these missions to the distant frontiers of our solar system, driven purely by the lure of the unknown and the fundamental questions about our place in the cosmos.
So, deep divers, we've really come full circle on this journey. From Neptune's whispered mathematical prediction, this ghost in the machine of the solar system, to Voyager 2's breathtaking yet tantalizingly brief flyby. Neptune remains this realm of incredible paradoxes. It's a dynamic giant, home to the fastest winds we know of, yet it's cloaked in this tranquil, almost serene, deep blue. Its moons, especially the captivating Triton, hint at hidden oceans and maybe even a potential for life, while the planet Neptune itself is this crushing, frigid, violent abyss.
Our knowledge, as comprehensive as we've tried to make it today, is truly just that tantalizing snapshot. It's a brief glimpse that leaves these profound questions still echoing across the vastness of space between us and that distant blue world. We're still pondering the precise nature of Neptune's powerful internal heat source. What exactly is the engine inside that drives its impossible winds? We still yearn to identify that unknown atmospheric component, the chromophore, that paints its clouds that deeper, more vivid blue than its twin Uranus. What chemical secrets does it hold?
And what further secrets do the complete life cycles of its great transient dark spots hold? What will their coming and going finally tell us about the deep inner workings of these mysterious ice giant atmospheres? And maybe most profoundly, that astrobiological call from Triton. Will we ever confirm if a subsurface ocean truly exists there today? And could it possibly rewrite our understanding of where life might exist, not just in our solar system, but potentially elsewhere in the universe?
The journey to Neptune, both the past explorations and the future dreams, is really more than just a scientific endeavor. It truly is a testament to humanity's insatiable curiosity, our relentless drive to push boundaries, and maybe most importantly, our capacity for these incredible multi-generational endeavors that span careers and lifetimes. It reminds us that exploring our solar system, especially its most distant and challenging frontiers, isn't just about finding answers. It's often about continually expanding the scope and ambition of the questions we even dare to ask in the first place.
So we leave you deep divers with this provocative thought to ponder. As we continue to look out at that deep blue giant hanging in the darkness and dream of returning, what new knowledge will you seek out? What mysteries, big or small, will you help unravel, maybe in your own way, in the next chapter of humanity's ongoing deep dive into the vast unknown? Thank you for joining us on The Deep Dive.